Hi everyone, I am Neha from Mathematically Inclined, and today we are going to discuss the concept of differentiability of a function. All the chapters of class 12 have been uploaded in the form of separate playlists. The link for the same is in the description box below. Also, all these videos have been crafted not only to suit your CBSE needs but to give a perfect head start to your competitive exams as well. So let's get started. So beginning with differentiability at a point, we begin by saying let fx be a real valued function. By this we mean that the output or the range of the function is reals defined on a certain interval AB, and let C be a random point in AB. Then fx is said to be differentiable or derivable at x equal to c, provided limit x tending to c fx minus fc upon x minus c exists finitely. Please note, it should have a finite value and should not be tending towards plus or minus infinity. Or if I try to split it in terms of my left hand limit and right hand limit, by substituting x as c minus h for LHL and x equal to c plus h for RHL, these c's get cancelled and this is the final definition. Now, in order to understand the differentiability of a function at a certain point, let's explore its geometrical interpretation. So here I have taken a random curve y is equal to fx. I take any random point P with the x coordinate as c and the y coordinate as fc. Now I try taking 2 points in its neighborhood where h tends to 0. So q is c minus h f of c minus h, likewise r is c plus h f of c plus h. Now talking of the slope of this secant or the chord QP, so slope of QP, we say f of c minus h minus f of c upon c minus h minus c. So this gives us f of c minus h minus f of c upon minus h. Now please remember, as h approaches 0, your q also approaches p. This means limit h tending to 0 f of c minus h minus f of c whole upon minus h is tending towards the slope of the tangent at p, because as they coincide, as q becomes closer and closer to p, this chord actually ends up becoming a tangent at p. So tangent at p could be given by this formula. Similarly, for slope of PR, we get f of c plus h minus fc upon c plus h minus c. As h tends to 0, once again your r starts coinciding with p, which once again makes this secant PR to tangent at p, which is given by this formula. So for differentiability for a function to exist, LHL and RHL at that point should be the same, which gives us a unique tangent at P. So geometrically, when you say derivative of a function exists at a point, that means the function has a unique tangent at that point. Extending the concept of differentiability further, we talk of differentiability at a certain interval. So a function fx is said to be differentiable in, and we get two cases, open interval AB or the closed interval AB. Fx is differentiable in the open interval AB provided it is differentiable for all points within the interval AB. So that means, as in the previous definition, if fx is differentiable at all points of AB, then it is said to be differentiable in the open interval AB. For differentiability on the closed interval, the first point is that it should be differentiable in the open interval, and thus fx and then fx should be differentiable at the endpoints of the interval, which are a and b. For this, that means the right hand limit at a must exist finitely, and so should the left hand limit at b exist. This result expresses a very interesting relationship between differentiability and continuity. So, it says differentiability implies continuity. If I take a function fx equal to y, which is differentiable at a certain point, say a, then it is also going to be continuous at the same point a. Let's try proving this. So since given y equal to fx is differentiable at x equal to a, this implies that this limit exists, has a finite value which is given by f dash of a. So I mark this equation. Now in order to prove that fx is continuous at a, we need to establish that limit x tending to a fx is equal to fa. We know we can express fx this way by subtracting and adding f of a. Now, in order to use your equation 1, I will divide and multiply with the expression x minus a. So, we get fx minus fa upon x minus a into x minus a plus this fa stays as it is. Now, let's try taking limits on both sides. So, we get limit x tending to a of fx is given by limit x tending to a of the entire expression. And if you recollect your class 11, limit of fx plus gx is the same as limit fx plus limit gx. So this becomes, further this limit is applied on each of these expressions. So according to the first one, we get f dash a into, if I substitute x tending to a, this expression becomes 0 plus fa just being a constant gives us the answer as fa. This implies limit x tending to a of fx is equal to f of a. And well, that is exactly what we had to prove. Now the same theorem could be extended to the function is differentiable at a certain interval, then it is also continuous in the same interval, for which we would say let a be any random point in the open or the closed interval, repeat the entire process, and in the end conclude that since a was an arbitrary point, so the result holds for the entire interval. Yes, we have established that differentiability implies continuity, but converse need not be true. Now, whenever you want to say some statement is not true, then you have to supplement it with an example. Now, we take the example of a modulus function. Now, first, let's try to establish its continuity. So, talking of the mod function, we know it could be split this way. We calculate LHL of the function at 0 where the function is getting split. We calculate RHL of the function at 0 and we check the value of the function at 0. We see all three of them are giving us the same answer. Also for x less than 0 or greater than 0, we are getting a polynomial function. Thus, mod x is everywhere continuous. Also, if you try to recollect the graph for this, it's a V-shaped graph. That means you can draw the graph without lifting the pen even once. Now, talking of the differentiability at the same point, we start with left-hand derivative, which is given by this definition. Let's substitute the values. So, f of x will get minus x minus 0 upon x minus 0. We end up getting the answer as minus 1. Now talking of the right hand derivative, we take limit x tending to 0 from the positive side, and once again you substitute for the values, you get x minus 0 upon x minus 0, which is 1. As you can clearly see, your LHD is giving you minus 1 as the answer and RHD is plus 1. So that means the function is not differentiable at the point 0. Also, please note, geometrically mod of x at 0 can get multiple tangents. Whereas we had just discussed that for a function to be differentiable at a certain point, it should have a unique tangent. Now moving on to the questions on differentiability, have a look at the first one. The function has been defined this way and we need to show that it is not differentiable at the point 2. So to begin with, we start with LHD, which would be limit x tending to 2 from the left hand side, f of x minus f of 2 upon x minus 2. Since the function is different at both sides of 2, so we can directly substitute for the value. F of x becomes x minus 1 minus f of 2 would give us 2 into 2 minus 3 upon x minus 2. On simplifying the numerator, you get x minus 2 upon x minus 2 and the answer is 1. Now similarly, talking about the right hand derivative, let's substitute for the values. You get 2x minus 3 minus f of 2, which is once again 2 into 2 minus 3 upon x minus 2. On simplifying, you get twice of x minus 2 upon x minus 2, which gives us the answer 2. As LHD at 2 is 1 and RHD at 2 is 2, therefore the function is not differentiable at the point 2. Now looking at the second question, if fx has been defined this way, we need to show it is not differentiable at x equal to 1. Before we begin, we need to redefine our function fx. Talking of each of the functions, you know mod of x plus 1 could be split this way as x is greater than equal to minus 1 or less than minus 1. Similarly, mod of x minus 1 has this sort of breakup. We are basically trying to look at the points where your total function gets split. So from here, the points of split become minus 1 and 1. Let's see how we arrange them. Your fx would be divided under these three intervals. For x less than minus 1, the first function gives us minus of x plus 1 and the second function also takes this value. For the second one, where your x is greater than equal to minus 1, we get x plus 1 here. But it is less than 1, so we continue to take the second function. Similarly, for the third one, for the first function mod x plus 1, we take the first value, which is x plus 1, and likewise for the second function, we once again take the first value. On simplifying for each of the intervals, our new function looks like minus 2x whenever x is less than minus 1, 2 whenever your x is lying between minus 1 and 1, and 2x when x is greater than equal to 1. Let's take this further and continue with our question. Now to check for the left hand derivative at 1, we write the definition and then limit x tending to 1 from the left hand side gives us the second function. F at 1 gives us 2x, which is 2 into 1, and this is x minus 1. So we get 2 minus 2, which is 0. So limit x tending to 1, 0 upon x minus 1 simply gives us the answer 0. Similarly, for the right hand derivative, when you take the limit x tending to 1 from the right side, now this means it has to be the function 2x here. F at 1 is once again 2 upon x minus 1. Now taking 2 common from the numerator, the answer turns out to be 2. Now you can clearly see LHD at 1 is 0, RHD at 1 is 2. So the function is not differentiable at the point 1. Similarly, I leave it to you people to establish the non-differentiability of this function at the point x equal to minus 1. Looking at the third question, it says discuss the differentiability of the given function at x equal to 0. So once again, we split your function x mod x as for x greater than equal to 0, it becomes x into positive x, so gives us x square. And for x less than 0, it gives us x into minus x, which is minus x square. Once your function is ready, it gets very easy. So checking for LHD at 0 and then substitute for the values. Now limit x tending to 0 from the left hand side gives us this function. So minus x square minus f at 0 would be just 0 square upon x minus 0. Limit x tending to 0 minus of x, which is 0. Similarly for RHD at 0, once you write the definition, fx from right side of 0 is x square minus 0 upon x minus 0, which once again gives us the answer at 0. So this gives us that the function is differentiable at the point x equal to 0. Moving on to question 4, you have to discuss the differentiability of the greatest integer function which has been defined from 0 to 3 at the point x equal to 2. Please note you could be asked the same question at any other integral point or in general for all integral points. So at x equal to 2, if I start with LHD and put x as 2 minus h, where h is tending towards 0, this becomes f of 2 minus h minus f of 2 upon 2 minus h minus 2. This means this becomes limit h tending to 0 greatest integer function of 2 minus h minus greatest integer function of 2 upon minus h. Please note greatest integer function of 2 would give us the value 2. However, greatest integer function of 2 minus h brings us back to the value 1, which gives us the answer tending towards infinity. Likewise for RHD, we put x equal to 2 plus h, which gives us limit h tending to 0, 2 plus h minus 2 upon 2 plus h minus 2 over here. Now greatest integer function of 2 plus h, that means even if I add a very small value to 2, maybe it becomes 2.0001 or anything, the greatest integer function will bring it back to the integer value 2. So this becomes limit h tending to 0, 2 minus 2 upon h, which gives us the answer 0. As you can see, LHD is tending towards infinity and RHD at 2 is equal to 0. Therefore, the function is not differentiable at 2. The fifth question is a deviation from the usual kind of questions asked. You are given f of t is f of 2 is 4, f dash 2 is 1, and you have to find this expression. Let's get started. Your f dash 2 is equal to 1. So we apply the basic definition and say limit x tending to 2, fx minus f of 2 upon x minus 2 should be equal to 1. Let's mark this as one of the equations. Now let's look at what we have to find. I call this as the trick step because we would be adding and subtracting a certain quantity, which you would soon discover why. Add and subtract twice of f2 so that the same could be taken common from the first, second terms. So this gives us, if I take f of 2 common, x minus 2 here, and likewise, similarly, when I take 2 common from the third and fourth, we get fx minus f of 2 whole upon x minus 2. Let's separate out these two terms. So the first one only gives us f of 2, whereas the second term leaves us with twice of limit x tending to 2, f of x minus f of 2 upon x minus 2. And if you notice, that's exactly what our first equation gives us. So this implies the given expression gives us f of 2 minus twice of f dash 2. Now f of 2 as given in the question is 4 minus f dash 2 is equal to 1 as per your equation 1. So this gives us 2 as the answer for the given expression. Wasn't that easy? Well, this brings us to the end of this topic. I hope you understood the concept and would be practicing a lot of questions. If you found the video useful, please give it a thumbs up and take a moment to subscribe right away. Also share your feedback because your comments are important to me. I'll see you in the next video. Until then, bye-bye.